talking about these. So, just to recall, right, a monoid is when we have, there's some type, and it has this associative binary operation, and an identity element. If you don't have an identity element, that's called a semigroup. Don't worry about that, but occasionally there are situations where you do have an associative combining operation, but you don't have an identity. Maybe we'll see some examples of it, but in many cases, and intuitively, this kind of has to do with, think of this as like, it's all about accumulating information, right? So the empty thing, the identity, corresponds to like having zero information. And then every time that you use this operation, it's like you're combining, you're like, oh, I knew this, and I know this, and so now I know both things. Right? And the associativity kind of means that, well, right, it means parentheses don't matter. So it kind of doesn't matter. We're just taking a bunch of information and combining it all together. So we did a couple examples. So integers under plus, maybe the integer represents some information about, how many times you saw something, right, or you're counting. And so when you add, right, you're combining the information like, oh, I saw this thing 3 times over here, I saw it 6 times over here, so now I've seen it 9 times this way, right? A list, the information that you're learning is like, I don't know, it's a list, right? So it's just like, maybe it's like observation. So things that I have observed, in the sequence that I have observed them. And if I just first observe these 3 things, and then later I observe these 6 things, and I combine them, I now have my total observations. So these this shows up all over the place in computer science. And hopefully, by the end of class today, I'll convince you that these do indeed show up all over the place. We'll go through some examples, and I will also show you, I plan to show you some kind of concrete examples of where I've used these in some of my code, and kind of why they show up all over the place. Maybe if you've studied any, if you've ever studied any group theory, like if you've taken abstract algebra, a group has these things, plus it has an inverse operation. That, so like the integers with addition is a group because you also have negative numbers, and you can add 3 plus negative 3, and you get back the identity of 0. Those are not as common in computer science because the inverse of something is kind of like destroying information. It's like I had some information, but now I have like some anti-information, and when I combine them, I know nothing anymore. And that's kind of weird in the context of computing. Like, why would you want to destroy information? And so they don't show up as much. They show up a lot in math because it really is all about, in math it's all about symmetry. And when you have symmetry, it's like, well, if you do something, you can always undo it and get back to symmetric position. But if you're thinking about information, it doesn't really make sense to destroy it. Or typically, it doesn't make sense to say we always have a way to destroy whatever information we want. Of course, sometimes we throw away information. All right. So we'll do a bunch more examples, but I want to actually show you the real class. So it looks something like this, right? So we're in a class. I guess I already kind of said this above, but just to write it down. And then this has type 1. And then we also saw, there's also this class, well, basically, we also have this, which equals anything. Yeah, ambiguous, of course, right? Common design. I don't know, I'll call it, just so we can write down some instances. So let's just write down these instances that we have here. Monoid integer where f(n) equals plus and equals 0. Oh, said instance my monoid list of A, where my append is plus plus, and my empty is what are some other examples? So addition is not the only associative binary operation on integers. Can anyone think of another common binary operation on integers that's associative? Multiplication. Does it have an identity element? One, right. So that also is a monoid. So say or integers with multiplication of 1. So we actually run into a problem here because I can't, so if I try doing this, okay, it's going to yell at me. It says duplicate instance declarations. So I didn't tell you this before, but Haskell requires that if you have an instance of a class for a type, like you can only have exactly one instance of a given class for a given type. And the reason is that otherwise, if I used mappend somewhere on an integer, it's like, well, how do I know which one you want me to choose? Like, there's two different ones, so I can't. They have to be unique, so that it can automatically fill them in for you. Right? Otherwise, you would just have to write it yourself. You would have to explicitly tell it which one you wanted, and then that kind of defeats the whole purpose of having a type on it. So this is actually not allowed. And if we look in, so this is the way the standard library actually does it. So there is not actually a monoid instance for integer or for any numeric type. Instead, there's a couple of new types. So for example, there's a new type, sum A. It's something like this. Well, basically, I'm not increasing notation, so it doesn't matter. Have we seen new type before? No? Okay. So it's very simple to explain. New type is the same as data, except you only get to have a single constructor with a single thing inside it. So basically, it's just like the goal is that, say some integer is a different type than integer. Right there, sum is its own new type, and because sum just contains a single integer inside of it, at runtime it's just stored as an integer. So there's no runtime penalty at all. It's just like, I'm just declaring this so that I have a brand new type that I can talk about that's distinct from integer. One place this gets used is like, let's say that you had a program that needed to, there were some values that represented measurements in feet, and there were other values that represented measurements in meters, right? And it would be really, really bad. Let's say it was, say, the control program for, a space probe or something. Right? And this has actually happened. There was one, I think it was something going to Mars, and am I right? Yeah. And it crashed and was destroyed because there was one place in the code where there was like a function that was supposed to be getting a value, and it was assuming it was in, say, feet, but it actually was in meters, and so it just like was way off and it crashed. Because it was like, oh no, we're going the wrong way, fire the rockets, and it was like, right? So right, if you just represent your values as like, say double, well then the type system isn't helping you at all. You have to keep track of, okay, wait, is this double, does it represent feet, does it represent meters, what is it? You'd really like to have two different types, one that's called feet, one that's called meters, and if you try to add them or do something with them, the type checker is like, no, these are different types, right? But you don't want to have to make up a whole new data type. Like at runtime, you don't actually want to store like all this extra stuff, you just want to store a number. And so that's one thing that new type can do. You could make two new type wrappers around double and call one of them feet, call one of them meters. At runtime, they're just doubles, but the type checker now makes sure that you keep them separate. What we're going to use this for is, some integer is a different type give some integer a monoid instance. So for example, there's an instance that looks something like this. So we say, well, as long as, if A is some numeric type, then some A is going to be a monoid, where, you know, if I say some X and some Y, it's sum of X plus Y, and I'm empty, oh, I guess it's my, it's sum 0. Okay. And then we can make another one for product, right? We say new type product A equals product. I'm not going to write out the whole thing, but these are now different types, and you can kind of choose which monoid you want by wrapping it up inside of a sum of product. So these are actually in the standard library. Really, I should comment them out because it's going to go in. Okay. What are some other things that are monoids? Let's see. So we talked about integers. Well, not just integers, right? Like any numeric, anything that has plus or times probably is going to be. So doubles, you know, int, integer, float, kind of stuff. And then any kind of list, which includes like, you know, strings or lists of whatever you want. There is, let's see, another example is so there's another type in the standard library called endo. And a value of type endo A, endo stands for endomorphism, which just means a function from some type to itself. So a value of type endo A just has a function of type A to A. And we've seen we've seen things like this before. So for example, we were talking about like folds for natural numbers, right? You have this A to A function that you're going to run some number of times. And the point is, how can I combine two of these? Well, I can combine them by composing them, right? So I say, okay, if I have one function for A to A and another function for A to A, I can compose them into one bigger function from A to A. Right? And that is indeed associative, right? It doesn't matter how I parenthesize it, I'm going to get the same pipeline. It's not commutative, like if I switch the functions, I might get a different function. So it's going to look something like this. If I get endo F1 and endo F2, I'm going to get out endo of F1 dot. And what's the, is there an identity element? I'm looking for a function of type A to A such that when I compose it with something else, I just get that something else. It doesn't change it. What function is that? Amy? Right. The identity function is, well, it's the identity. It's the identity element for composition. Composing with identity doesn't do anything. What else? So we can now start, there's like various ways we can combine monoids. So for example, if A is a monoid and B is a monoid, that is, you know, I have a way to combine A's and I also have a way to combine B's. Then I claim that pairs of A's and B's are monoid. Right, and how would I combine two pairs? So if I have a, you know, a pair of an A and a B, another pair of an A and a B, I just kind of line them up and I combine the A's and I combine the B's separately. So this is like, it's kind of like combining monoids in parallel. That's how I think of it. If it's just like I've got this one thing I want to keep track of and I also have another thing I want to keep track of, I can kind of bundle them up together and be like, oh, I'm keeping track of both these things. And I can, so we'd have something like, well, my MMD, it's just going to be, just an empty thing for both. And then if I have A1, B1, A2, B2, I just say A1, okay, makes sense. I'm going to show you one more example. This one is interesting. Well, actually, before I do that, so for example, if I said, sum 3 divided by 6. So remember, this operator is just a synonym for an append. So I've got two pairs, and then I'm using, on the left side, I'm using a sum wrapper around, I guess, an int. So it's going to add the int and it's going to multiply the things. So, okay, well, it's got this extra syntax there, but basically it's sum containing 8 and product containing 12. There's also things like, before I get to that other example, there's a few kind of functions that the standard library provides for working with any monoid. So for example, there's a useful thing called mconcat that says for any monoid type M, if you give me a list of M, it will reduce it down to a single value type M. So how does this work? I mean, right, we get this mappend thing that can combine two things into one. So if I have a whole list, I can just kind of do that repeatedly, right? So I think it's actually defined as, fold R mappend, right? So if it's an empty list, you get that identity element. And otherwise, you just do a fold with combining with mconcat. So that, so then I can do things like mconcat, if I have like sum 5, sum 6, sum 2, just adds them up, right? So as a similar kind of example, but if let's say I just had this list, 5, 6, 8, 2, and I wanted to add everything in the list. Now, there is actually a standard library function called sum, but let's say there wasn't. Like all I had was the monoid. I could say, mapped sum, so wrap them all in a sum wrapper so that I know that I want to add them. Then do mconcat. And then I guess I'll call get sum to like extract the result from the sum wrapper. So that's one. In this case, it's a slightly kind of Baroque way to add up a list of numbers. But if you have some other monoid that's not like, it just so happens that sum is so common that there is a function that just does this already. But if you had some other monoid, or maybe even a monoid that you made yourself, and you wanted to have a bunch of things in the list and combine them, like you could do this kind of thing, use mconcat. There's also like, so there's also some useful fold map. Essentially has a type like monoid M. So this, I'll let you look at the type for a second. Anyone tell me, just from the type, what do you function from A to M, and it takes a list of A, and then it gives you back an M. And the type M has to be a monoid.
Takes a list.
Yeah.
That's kind of confusing.
Yeah, I mean, how does it do that though? Like what does it use this function for? I mean, it might be a sum, but it's not specific to that, right? It could be for any monoid. Jack?
Is it mapping, is it kind of something like M map and M concat together?
Yeah, so you mean like it's mapping this function over here? Is that what you're saying? Yeah, and that would give you a list of M's, and then it does the M concat thing? Yeah, exactly. Yeah, so really, it's nothing special in one sense. It's just, if you give it a function f and a list of A's, it just does M concat of map of A's, which we could also write as but again, it's a common thing to do, and so this is provided. All right, let's see one more instance. Let's see if we can kind of work out how this would work together. So I claim, so we've seen, some basic types like numbers, even like things like this, pairs. But what about functions in general? So this is one way to make a monoid out of functions, if you specifically have a function from A to A. But there's there's a different way to do it. It's more general. So if I say, so I claim that as long as I can combine, as long as B is a monoid, as long as I have a way to combine B's, then I can actually combine functions from A to B. So let's work through this. We'll think about what the types are and how we might do this. So my M append, right, is going to take a function from A to B and a function from A to B and return a function from A to B. Right? If I combine two functions from A to B into one. So we'll call them F and G, or maybe F1, F2. So, and I now have to output of an underscore. It should tell me, yeah, found all A to B. So I need an A to B function. So any ideas how I should start or what I might do? So first of all, if I want to make a function of some type, how do I even start? I can start making the function without even thinking yet about what it does. So yeah, exactly. So I could say, well, okay, I need a function from A to B, so I might as well make a lambda. It takes something of type A, and then it has to return something of type B. Okay, so I need a B. How can I get a B? Let's thing I could do is I could just like call F1 on A, and that would give me a B. But that doesn't seem quite right, because then I'm just ignoring F2. So in what sense am I combining F1 and F2? So somehow I want to use both F1 and F2. So any of these? Right. So I could call F1 and F2 both on A, and then combine their outputs, right? Because I know that B is a monoid, so I can combine those B's that I get. So F1, right, so what is this saying? This is saying, look, to combine two functions, you get the function that, you know, runs both and then combines their outputs. What would be M-empty? So M-empty has to just be something of type A to B. And, right, in theory, it should be the function that when we do this M of n thing, it doesn't change. I mean, but if we just think about the type, we can, there's like not many options we have here. So we have to take an A as input, right? But I don't know what A is. I also don't know what B is. Like, it could be any types. How could I possibly output a B? Where could I get a B from? A value of type B that I can output?
Calling MFT.
Exactly. That's the only thing I can possibly do. The only thing I know about B is that it's a monoid, and that means there's an empty empty thing that I can use. That also makes sense, right? The kind of empty function is the one that ignores its input and just always returns empty. Right? If you combine that with some other function, it's not going to change it because you're just always combining the output with empty. So nothing happens there. So right, that's that underscore. And I don't need to read that in. So for example, you know, let's say that you have this is a little bit contrived, but it kind of illustrates the idea. Let's say that I've got three different methods of giving like a score to a string. So score functions. So maybe like one is the length of the string. Another is, you know, the number of vowels. So like length dot filter. And maybe another one is like the ASCII value of its first letter. I'm just making this up, right? So, okay, so those are three. And if I ask, you know, what's the type of score functions? It says, yeah, it's a list of functions from strings to ints. So it's a list of these scoring methods for a string. And now, for whatever reason, let's say that I want to say, okay, the meta score for a string is you just add up all of those different. You say, okay, you take the length, you take the length, the number of vowels, you take all those things, you just add them up, and that's like the total score for the string. One thing I can, and actually, you know what, I should say, well, I could say something like, you know, meta score equals m concat. So I can't just say m concat score functions because int is not a monoid, right? We have to, it's like, well, do we want to add, do we want to multiply, what do we want to do? So I want to say something like, you know, map. So I'm basically going to say, take each of those score functions and compose it with, like, wrap the output in sum. And then take all those functions and combine them. And that gives me one function that will run each of those functions on the input and then combine all the outputs. So, right, metascore is just a function from a string to some int. So like, you know, if I say like, 11. And we can, let's think about this. So the length of hello is 5, the number of vowels is 2, and the order of H is 104, so 104 plus 7 is 11. Right? Again, that's a little bit contrived, but maybe you can see that, like, and I've wanted to do this. There's been times when I've had, like, a collection of functions that all operate on something, and I want to combine, I want to, like, run all of them and combine their results. And you could do that manually by just saying, like, you could literally say that, but it's actually just combining them according to that monoid. Here's one other cool monoid, and this has some cool, some cool things you can do correctly with this. So there is a data type in the standard library called ordering, which is I think we might have seen this in passing the other day. So basically, it just has 3 values. Oh, it doesn't like it because, yeah, I got comments down. That's in the standard library already, but just like bool has 2 values, this is just a type with 3 values. They're called LT, EQ, and GT. And for example, there's a standard function called compare that does something like this. I think I mentioned this the other day. So like if we say compare 2, 3, it says, oh, 2 is less than 3. If we say compare 3, 3, it says, oh, they're equal. If we say compare 4, 3, it says greater than. Right? So it's kind of telling you those 3 possibilities, like which is it. And we can make ordering a monoid. The way this works is, so what could we possibly mean by, like, combining things here? The idea is this. If you imagine, let's say you're comparing, like, 2 words letter by letter, to see what order they come in the dictionary. If they're equal, then you don't know yet. You have to keep going and look at the next letter, right? But if one is less than the other, or one is greater than the other, right, then you can stop and say that's the answer. Like, this word, since this letter is less than this letter, this word is less than this word. I don't need to look at the rest of the letters. So that's the intuition here, that we say, okay, look, if you see a less than, then it doesn't matter what comes after that, the answer is less than. Right? Less than kind of overrides anything else because we're done. If you see greater than anything, then you just return greater than. But if you see an EQ, you just return whatever the other thing is, because EQ kind of doesn't tell you anything yet. You have to just say, well, whatever the answer is for the other case. Does this have, an identity element? Yes, it does. Clearly, EQ is the identity element, right? Because it says it right here that EQ combined with anything gives you that other thing. It would also work if you put EQ like here, right? Okay, so what does this let us do? This lets us do things like let's say I want to compare 2 strings, but I want to kind of make up my own custom comparison method, right? So I don't just want to use dictionary order. So I want to say, okay, first of all, if one is shorter than the other one, then I first just want to compare their lengths, right? And like, we'll just say shorter strings come before longer strings, right? Doesn't matter what their letters are, I just want to compare their lengths. And then if their lengths are the same, then I want to compare like how many vowels they have. And if they have, if one is less vowels, that'll be less. And if they have the same number of vowels, then I'll compare them alphabetically. Right? I made that up, but so we want to. function called comparing that we can use. It just says, so let's, I guess my letters are in the opposite order. Right. So what does this mean? This function says, ultimately we want to compare two things of type B. So we want to say, give me two B's and then I'll give you an ordering. I'll tell you like, this one is the first one less or equal or greater than the second one. But I want to compare them, according to some, I don't just want to literally compare them. I want to say run some function on each one and that'll give you some value and I want you to compare them according to that value. So, for example, in our example here, if I want to compare two strings by their length, I could say comparing length. So this function would be length that says, run length on each string, that'll give you an int. And then I want you to compare those ints, and that's how I want you to compare the two things. So comparing f is, you give me your first B and your second B, and then I'm just going to say compare fb1 and fb2. So don't compare the b1 and b2 directly, compare the results of that function. Right? So, for example, if I say comparing, if I just say compare hello hi, it says less than because hello comes before hi in the dictionary. Right? That's like the standard way to compare strings. But if I say comparing length, hello hi, now it's going to run the length function on both and compare those. And so now it'll say greater than because hello is longer than hi. Okay? So we almost have all the pieces. So the one last thing to notice is, notice that ordering is a monoid, right, that we defined up here. We also know that as long as the output type is a monoid, then any function to that output type is a monoid. So basically, if I have functions of this type, b to ordering, I can, that's a monoid. And so I can say my str compare is going to take two strings and give us an ordering. And I want to say, first, compare their length. Actually, I can even say cat. First, compare their length. Then we're going to compare length.filter is vowel, so the number of vowels. And then we're going to just compare them. I have to import. If I wanted, I could also, I don't know, I could have, maybe I'll write it this way actually. Either way, I could write comparing length, I could write mappend this, or I can just put mcat. So it's worth thinking through again how this works. Well, so let's just see that it works, and then we can think more about how it works. So if I say my str compare, so this should say greater than because hello is longer than hi, and that's like the first thing that it looks at, right? But let's see, if I have about hello and happy, so maybe that's not a good example because about hobby. So they have the same length, so it should move on to compare them by the number of vowels. And now I didn't define y as a vowel, which maybe I should have, but whatever. Given that definition, hello has more vowels than hoppy, and so it should say greater than. And then, I don't know, if I change that to an I. Now they same length, they have the same number of vowels, so finally it should fall back to comparing them by dictionary order, which now it should say less than, because hello comes before, HE comes before HO in dictionary. Okay, so how does this work? Well, first of all, we have a bunch of functions here. These are all, each of these is a function of type string to ordering. And so it says, okay, M can count all of these. That means we're going to take all of them and run all of them on the same two input strings. They're all going to return some orderings. And then we're going to combine those orderings using the monoid for orderings. Right? And that one, that says, you know, as long as you keep seeing an EQ, just keep going and look at the next thing. But as soon as you see an LT or GT, just return that. And that's what we want, right? So as soon as we see, as soon as the first thing that says, oh, it's for sure less than or greater than, then we stop. But if you see an EQ, then it's like, well, we don't know yet, so keep going, look at the next one. Anyway, this is just a nifty trick that, I mean, I've used a bunch in practice. Like, it's pretty common that you're like, oh, I have this way that I want to sort these, I want to sort some things, but I don't want to sort them according to like the usual order that you would sort them into, because I actually want, you know, shorter things to come first and then longer things, or whatever. You can just very easily throw together your own custom little comparison function. And in fact, there's a function called sort by. Right, so sort by, the standard sort function just assumes that you're giving it things that have an ORD instance, so it'll just compare them normally. But sort by takes an A to ordering function, so you can give it whatever custom comparison function you want. So we can even say L.sort by my str compare, and then, you know, yeah, so the shortest thing comes first, right? And then, okay, then something with length 3. Then all the things of length 5 come after that. In order first by number of vowels. So these have the least number of vowels. And then this is out dictionary ordered, right? And then, yeah, so we can do a custom sort. We are, let's see, we're almost out of time. Let me just show you, and maybe I'll show you a few more next time because there's more interesting things to say about this. But just if I can show you just like a couple places that I've used monoids for serious in my own code. So this is this game that I made over my sabbatical, and maybe you saw this. Something I think came to my talk. But it doesn't matter what it is. The point is. It's a custom language, and when you parse the language, you want to keep track of, you know, for each thing that you parsed, you want to remember where it came from in the input, and that helps you give better error messages. If something goes wrong, you can say, oh, there was an error on line, you know, 24 from characters 6 to 18. You know, here it is. And so here it is. I'll make this bigger in a second. Yeah. So there's this data type, location. Okay, location represents the location in the source code where something came from, right? And so there could be no location. Maybe we don't have any information about what the location of this thing was, for whatever reason. Or these two ints represent, you know, like the first character, the position of the first character, and or the index of the first character and the index of the last character. So if it started on, you know, at character 20 and it went till character 32, let's say 2032. And right, this is the interesting point that well, I defined semigroup, which just defines this operator, and then also monoid, which right? This is the way to combine them, and this is the empty thing. So first of all, node location is the identity. If you don't have any information about the location, then it doesn't change anything, right? So we just say, these two lines. But then how do we combine, if I have two locations, the idea is, I have something that came from here and something that came from here, and I'm combining them into a bigger thing that represents like both combined somehow. And so I want to combine their locations. How do I combine locations? Well, I say, look, take the minimum of the starting location, right, and the maximum of the ending location, and that will give us a range that includes both of them. And it doesn't matter which order they're in. I'll get the same range either way. Right, so this gives us a really easy way to, as we're parsing individual little pieces, we like make these little small locations that correspond to each, but then as we build them up into bigger and bigger pieces of syntax, building up a syntax tree, we're combining their locations. So, if I want to know, like, where was this whole entire function definition, where was that? I have a location attached to it that I got by combining the locations of all the things inside of it, and it tells me the start. So we've talked about context. Like a context is like a map from variables to their types. So right here, a context is just a map from variables to anything, actually, because it's not just types. It could be like values. It could be other information about variables. And well, like maps, a map from a variable to something is a monoid, where empty is the empty map, and combining them is map union, where you just say, oh, I've got some information about these variables, I've got information about these other variables, I combine them, for whatever reason, I now have information about all the variables. This is another map kind of thing. It's like, there was one other. Oh yeah, here's a comment where I'm like, oh, we should use a monoid, but we're not right now. Anyway. So maybe I'll show you a couple of examples next time, because there's other interesting things, but these do show a lot. All right, any questions? So there's no monoids on the module that I just posted, but there probably will be on future monoid. All right, see you all on Friday.